So just to recap, we represent quantum gates or quantum circuits, which are the quantum analog of the classical logic circuits that make up computation by acting on individual bits in much the same way. Wires represent qubits. They pass from left to right. You think of this as a black box which performs the operation prescribed by the gate, and then out comes a newly transformed qubit. Just for the sake of the recording. Now, the measurement operation is a valid one that we can have on qubits, right? And so it needs a special, almost like a quantum gate notation, except this time we understand that this is the operation of, all right, measure this qubit, which will collapse its state. That's what that looks like. And we'll see them put together very shortly. Okay, so how do we actually start building these, right? Well, you could physically construct a quantum computer to do so. But that is a massive undertaking, and we're all working very hard to do that. So instead, we can simulate a quantum circuit using our regular classical machines. And this is possible with the help of certain tools that we will use throughout the rest of the camp, right? So we're going to be using qskit to do this today and later on. Yep, there are very nice drag and drop visualization tools that you don't actually need to write any code to use. But at the end of the day, we still have to make this run on classical computers, right? If we could execute the exact operations in the exact order the same way on a classical computer, we wouldn't need to build a quantum computer. So in fact, this is not very efficient, right? Simulating quantum devices on classical machines using the classical rules of information and computation is very inefficient, which means that we are very limited in the size of a quantum circuit that we can actually simulate, right? Once you get to a circuit which is complex, a quantum circuit which is complex enough to perform a very useful calculation, such as tell me what the energy of this molecular configuration is, right? I have some complex molecule and I want to know what state has the lowest energy or what that energy is. That might be something useful for a scientist, a chemist, an engineer to know. But the circuit that would require, the complexity of the circuit to perform that operation is so complex that it like the traveling salesman problem, actually performing that computation classically is just not possible, right? It's just not feasible. So even simulating quantum circuits falls into that category. And so we can only do very small systems to really debug our codes with debug our quantum algorithms in the simplest case and hope that there won't be a bug on the useful system size. That's the state of things right now. And this is possible because you might remember, really all of these operations are just matrix algebra, right? It's just perform this matrix multiplication on this initial vector. It gets pretty complex, but and we can't do it in the exact scaling of a quantum computer, but we can perform this calculus, right? We can calculate this. So that's what we do. So let's get started, right? So we're going to write our very first quantum program, and it's this is going to be a very simple one. All we want to do is create a quantum circuit that puts a qubit from initially the pure zero state into equal superposition and then measure it. As you can imagine, all we have to do is write 3 lines of code to do this. So step 1, when I say qskit is a tool implemented in Python, I mean that it's a package which we can import, right, to use in our code. And all you have to do to get started with that is write this line in your code cells. Now we have to create a quantum circuit object, much like how we very briefly got into classes. Basically, we first need to tell Python that we have an object which follows the rules of the quantum circuit, as prescribed in qskit. And so we have to start by creating one. In this case, we want 1 qubit and 1 classical bit. Okay, so that's what this line is saying. And all we're doing now is telling it, okay, I've created my quantum circuit object, circ. Now apply a Hadamard on the first qubit, right? why do we want the bit, the classical bit, right? So we want the classical bit so that we can record the result of the measurement of the qubit, right? It's not involved in the superposition or anything like that. It's just it's basically like create a quantum circuit with a qubit and then give me a piece of paper so that I can write down what the result is when I go to the measurement. Okay, so let's get started with that. Yeah, so that's my understanding is the same thing. What does zero input represent when applying the Hadamard gate? That represents the location of the qubit, right? So if I had many qubits in my quantum circuit, then I would have to tell my circuit which one do I mean when I say apply my H gate, right? And so in Python, many things index from 0, or they start counting from 0. So this means the first qubit. So let's see what we've done so far, right? Good to go. So we have our classical bit sitting waiting to record what the measurement is. What about the state 0? Okay, first Miles. So if I did circ H1, it would try to apply to the bit. I think it might throw an error because it knows that, yeah, it knows that you can only perform, quantum gates on qubits. And so if you try to say apply it to the to qubit 1, what that means is the second qubit, right? And it just throws the error, oh, you don't have, that qubit doesn't exist. So, you'd have to do something like this. And we're good to go. But that's not the algorithm that we want to implement. What about the state 0? So I don't think I understand that question. So we're constructing our quantum circuit and we're telling Python that this object is the circuit and it has a Hadamard gate on the 0th qubit, right? That's all we've done so far. And by the convention that I kind of mentioned, okay, great, yeah. So we do not have to tell Python, or we do not have to tell Qiskit that we want to have that qubit sit in the 0 state at first. So that's represented here when we draw the diagram. That's when we say that's the conventional way of doing things. That's the default. That's implied. Okay, not sure what the parentheses do in H. Yes, that's exactly right. Thanks. So yeah, Miles, you say apply Hadamard gate, and if I had 2 qubits, the quantum circuit needs to know which qubit to apply that to. So that's what the parentheses are. That's right, and you start from 0. Okay. Okay. So we've got our torch circuit built up. Now all that's left to do is we want to measure it. So we've successfully constructed, this is a real model of one of the most basic quantum circuits you can get started with, right? Is all I want is a circuit that prepares me a qubit in equal superposition, right? 0 and 1. So let's go ahead and measure it. And to do that, just like applying the Hadamard quantum gate to my circuit, I need to tell it to add the measurement object to the circuit. And here, like Lorraine kind of mentioned, the second number is the number of outputs, right? And when I say classical bits acting to record any possible measurement, that's what I mean. They're outputs of whatever measurements on the qubits, but that information is purely classical, right? You're only ever going to get back a 0 or a 1. And so you can just write that into a classical bit, right? Like an empty jar, if the qubit was measured to be 0, a full jar, if it was measured to be 1, that's a classical bit. Okay, so, and that's what this looks like. So here we're saying perform the measurement on the 0th qubit and record that into the 0th classical bit, right? So everything is initialized in 0, and this means change the state of the classical bit to whatever the outcome was on my qubit, the outcome of the measurement. And so if this gets put into equal superposition and then is measured to be in the state 1, this object is going to write that result, right? It's going to change the state of the classical bit to be 1. Okay, so that's what we mean. So this is our very first quantum circuit. Okay, so let's go ahead and execute this, right? So all we've done so far is build up this object, and we see how it gets drawn out at each step. So what happens if I actually run it? Well, first of all, what do we think is going to happen? Hopefully, I'm not beating a dead horse here. By equal superposition, half the time, this qubit is going to be measured in 0. Half the time, it's going to be measured in the 1 state. So to do that, we don't want to get into too deep into the weeds here, but we do actually need to, execute this circuit somehow, right? And so first we have to tell Qiskit, by the way, don't try to run this on a real quantum computer. This is a simple case. Go ahead and just simulate it. We can run this on a classical machine. So first I have to do that. Then I can actually run, right? I can execute my circuit using the simulator. And let's say, because this is going to give me a random output, right? If I just run it once, I'm not going to see the whole picture. I'm not going to know exactly what the probabilities were. So, I can see that first. If I only run for one shot, then when I go to print my results, I see that this time I got, my result was the qubit was in a 1 state, right? Finally, I've got one result where the qubit was in the 0 state. Okay, but I don't want to sit there and do that every time. So now I'm going to tell it just run 1,000 times, right? And keep track of all the results. When you execute this circuit, simulated, run it 1,000 times. All right. So now in one simulation, I see out, oh, by the way, about half, 499 of the times it measured 1, and about half, 525 times it ran 0, So, I can sit here and be doing this, and we can convince ourselves that this is a random process. That's really the point here, right? So we've built our very simple quantum circuit. We understood from the tools that we built up so far in the camp what was going to happen, and now we see that we can actually get this running in Python. So if the details of this are, if you're saying, well, that's kind of like a lot of code, and I'm not going to remember all that, that's totally fine. We will have a lot of example code so that you just have to worry about the important stuff. And the syntax of Qiskit just takes practice to remember exactly what exactly these commands are. So don't worry about that too much. Okay. Any questions so far? Yeah, you're not sure why we need the classical bit? For sure. So it's kind of like obvious, right? So why include it, right? Obviously, we're going to have to write down the result of my measurement somehow. But I think this is particularly useful when you're in the lab and you have a physical setup, just to think exactly what resources do I need. So you have a computer. Obviously, if I'm simulated, it's going to record the number of outputs. But in this case, if I want to keep track of this classical information to do something later on in the circuit, right, then I want to keep it included. So maybe I'll have some more complicated logic down here that says, by the way, if the first measurement result was a 1, perform this quantum gate. If that first measurement was a 0, perform a different one, right? And so it's useful to keep track of that classical information in a bit within the circuit as well. How are we transforming it to classical through physical wiring? Yeah, so this would have, it depends on your hardware exactly. But for example, you can measure the polarization of a photon, and depending on that, you can clearly distinguish and create a small procedure that says if it looks like this, change the voltage on this wire to high, and that means I've recorded that was a horizontal photon or something. But you record it physically, yeah. But in actual quantum computers, how do you combine classical and quantum bits together? Yeah, that's a great question. So there are ways of doing this, right? So it could be as simple as saying, right, like I have a physical object that represents a Hadamard gate, right? And I'm going to use the classical information, yes or no, to tell my lab tech, move it or don't move it, right? More abstractly, right, you can just think of if-then statements being valid for if classical condition, then execute quantum operation, right? That we will have access to. Yeah. Does the Qiskay simulator also simulate quantum errors? An example? Yeah. Well, Ben, so this is actually a really good point, that this simulator does not simulate noise. This does not simulate error, right? So when we say noise, we mean like random error that has nothing to do with the laws of the deterministic evolution of quantum systems or anything like that. It's just, somebody walked by, bumped the table and nudged my qubit in the wrong way or something. This does not simulate that. So yes, precisely. So the whole point is that this really is in an equal superposition, right? Like when there is no definite answer until the question is asked, and quantum mechanically, it's going to pull randomly from from the amplitudes, right? According to the amplitudes. And so, yeah, you should, if you got exactly 512 each time, you would be suspicious about the conclusion that quantum mechanics truly says everything is random, right? It's almost like there's some coordination. Cool. Okay, so let's proceed. And we'll see more examples going on. So we'll have plenty of chances to play with this. Okay, so we've got our very first quantum program. So after applying that Hadamard gate, we now see that the qubit that I sent in, which was in the state 0, now is in my equal superposition. And as we've kind of already discussed, the amplitudes are not observable directly. All you can do is measure the state of the qubit, and all the information you will get when you do that is I saw a 0 or I saw a 1, right? Right, so Jacob, so the Hadamard gate takes 0 to this plus superposition, and it takes a qubit which is in the 1 state to the superposition, equal superposition with a minus sign. So we'll see that later. Yeah. Great. So, and these amplitudes can't be observed directly. All you will ever see is, measure the qubit, and I see 0 or I see 1. And the reason that we wanted to run this a bunch, as we kind of saw, was to tease out that information with a single execution, right? Like this is going to be a probabilistic state or a probabilistic outcome when I measure it each time. So run it a bunch of times, and then I can get a picture of what was happening at that point in my circuit, right? And then I can be reasonably confident, okay, so the amplitude square of the superposition coefficients were roughly 50-50, right? What's the difference between a plus and minus superposition? Yeah, so that is, we'll see it later, but it's a mathematical distinction, right? That says that distinguishes two real physical states. A qubit can be in this exact superposition with the plus sign, and it can also be in the superposition with a minus sign, and that is a physically different situation. And we'll see that even though you cannot measure that difference at that exact moment when they are, if you have two qubits which are in those two superpositions, it will, like, the way that they transform under the same operation later on will be different because they started in with a different relative phase. That's what that's called. A different relative phase of -1 in this case. Okay. So we can plot our histogram, right? And before that, this just converts those counts out of 1024 into percentages. So roughly half the time I got 0 and half the time I got 1. But you can never, you have to use some statistics thinking, because you know that these are inherently random processes. So this is not going to tell you, no matter, well, definitely not for a small number of shots at the execution of the gate of the circuit, that the amplitude squared was exactly 0.511, right? then you have to think about, you know, these statistics concepts of like, yeah, noise and standard deviation and all that, but we won't get into that. Okay, great. So let's write another simple one, right? So this time, hopefully, you know, we're not surprised when I want to do the exact same thing, but swap out my Hadamard with what's called an X gate, that we're going to get something that looks very similar, right? So I think we did get to a general description of the X gate, but so what do people think is going to happen once I measure my qubit right here? What are my outcomes going to look like? No? Yep, it's always going to output 1, exactly. Great, because the X gate is equivalent, right, to the NOT operation. It just flips the bit. Okay. Excellent. Okay, and so like we said, how do we, you know, what's the difference between a plus and a minus sign in the superposition? Well, that's, you know, we keep saying, and now we're going to see that this is a detectable difference based on how they transform going forward. At this moment, you can't measure them, these two states, and see a difference in the outcome distributions. However, you can transform them using the exact same transformation, and they will behave differently, right? So we're going to be able to detect that difference in this way. Yeah. All right, so let's get started. So first, let's build a gate which initializes our qubit into the 1 state and then performs the Hadamard, right? So this is kind of what I was hinting at. You never have to tell the quantum circuit to initialize your qubit in the 0 state. That's the default. That's what's going to happen. If you want to perform some operation on a different state, right? In this case, we want to be working with a qubit in the 1 state. Then you just add on to your circuit to make that the case before you pass it to the gate that you're interested in. Okay, so let's see how we can use this to see a difference between plus and minus superposition states, right? So we're just going to measure this, right? So what are these two gates in sequence going to do? Right. First, we're going to, like I said, we're going to put this in the 1 state, and then we're going to apply the Hadamard gate on a qubit initialized in the 1 state. And this is going to give me the equal superposition with a minus sign, right? And if we measure that, we get about half zeros and half ones. So just reiterate, this is the circuit which constructed a superposition with a minus sign. Whereas before we performed, when all we did was add a Hadamard gate to the 0, we've created a superposition with the plus sign. So they're the same. Okay. Okay, so we've created 2 circuits. In this case, if you square root the frequency of that result, you get an approximation of the amplitude squared. Sorry, Lorraine, what?
I'm sorry, I can't type fast enough. Were you saying that if we apply a 0 to the Hadamard gate, we get a different output than if we apply a 1?
I'm saying that we get different physical states, yes. So the Hadamard gate transforms a qubit, which is in the 0 state, into an equal superposition with a plus sign.
Oh.
Right, and the Hadamard gate this is the same operation, but it transforms 1 state qubits differently, right? They act to send qubits which are in the 1 state to an equal superposition with a minus sign.
Okay, and we cannot measure the minus sign there in the physical output.
You can, yeah, exactly. So if it's at this point, right, you measure, all you're going to get is the frequency of zeros and the frequency of ones. And you're not going to be able to, yeah. Thank you. So Q in the diagram is the qubit. And the C sub 0 means this is the 0th classical bit that I include on my circuit. And yeah, if I make sure that my measurement is before I actually draw it, then you'll see that we're doing the same thing. Okay. Yeah. Yes, so we're going to see the difference between the plus and minus in the Hadamard in a moment. Yeah. So, something else that we can notice is what happens if I add another Hadamard onto the same qubit, right? Does anyone know what will happen? I think it's 50-50. So Ben has it. So the Hadamard is its own. We say that it inverts itself, right? It cancels itself out if you perform it sequentially. So this time it's 100% 1, right? So we started 0 in the 0 state. We flip ourselves. We get into the equal superposition. However, the Hadamard cancels itself out and we get 1. So we can start playing around with this however we want. And so the point really is that, the Hadamard gate, I want you to be thinking about how it transforms states in 1 and states in 0. Okay, great. So let's table that. So now let's look at another very simple circuit, but this time we're going to be looking at more than one qubit, kind of like what we played around with already, right? So you could imagine just the exact same thing as our very first circuit, where all we did was apply Hadamard on qubits, which we didn't do anything else to, so they started in 0 state. Now just do it twice, right? Just have 2 qubits, and now our classical bit register, right? Our sideline place to write the results of quantum measurements. We have 2 of them, right? We're going to keep track of, because we might want to keep track of both qubit measurement results. Okay, so what are the outcomes that are possible for each, or for the total result of the circuit if I measured right now after this? Right, so I have qubit number 0 and I have qubit number 1, and they are sitting in this configuration. Yeah, so each qubit has a 50-50 chance of being measured as 0 or 1, right? So in this case, half the time that qubit 0 is measured, we get a 0, and half the time it gets a 1. And half the time that qubit 0 is measured as 0, qubit 1 is also measured as 0, and half the time it's also measured as 1. So that means that we have 4 possible outcomes. They're both 0, 0 and 1, 1 and 0, and 1 and 1. Right? And they're acting independently. Yeah. So okay. So this is what quantum circuits look like, and we can ask ourselves questions about. So I perform these operations on my qubits. What do I expect to happen? What are the states at any intermediary step? And as we're going to see, we can put them together to do something, right? So this is the formalism, and these are the tools that we're going to be using. And there'll be plenty of time to get used to these commands as we're going to work on some problems. There are plenty of chances to review in the notebooks. So we will be using Qiskit, which you have to follow the following steps to actually interact with quantum circuits, right? First, import everything and create your quantum circuit. You add gates as you would like by telling Qiskit where I want to apply each gate. You can then add measurements, which will then be encoded into classical bits sitting on the sideline of your circuit. To actually execute that, you have to first tell your circuit, or you have to tell execute this. In most cases, for us, we will just be using a backend that is a simulator on your classical computers. But if you would like, the process is the exact same for executing this on a quantum computer offered by IBM, for example. You would just have to tell it, instead of saying use the backend simulator, we would use the label of a particular quantum computer offered by IBM. What is the object air and what is the backend? So yeah, so air is a subcomponent of Qiskit, which hosts these simulators, right? The backend object is what you are going to use to execute your circuit, right? So when we say, you can think about this word as being equivalent to the executor, right? In this case, it's going to be a simulator, which is technically from the air subpackage of Qiskit. Or you can just think about it as, in the example code, this is what is going to actually execute it, right? You don't have to worry about that, the details too much. But right, so a backend could be a quantum, like a physical quantum device hosted in a lab somewhere. And it would work very similarly. Okay, and then you just have to tell Qiskit, okay, now I've told you what executor I want. I've told you the circuit. Go ahead and run it, right? Execute it and record the results. And then after that, you will have your object, which contains the results. And we've printed them for ease of visualization in histograms. You can, then you have your data, right, of what the quantum circuit actually did.